Let me start recording. Okay, let's see. You can see my PowerPoint screen, right? Hopefully you can see that. At any point during the lesson, if you do have a question, feel free to text it in the messaging box. I will be checking that frequently. When I hear any sound, I'll be looking at it. Yeah, for some reason, less people are showing up, but then they're asking me later on, where's the recording? And I'm like, well, if nobody shows up, I don't record because there's nobody to. So, yeah. Anyway, we're starting with chapter 5. So, exam 1 covered chapter 2 and 3. Exam 2 will cover 4, 5, and 11. So let me see. Since we have 2 days to go over this chapter, my goal is to get about halfway through, and then we'll do a little detouring since it's just us right now. Okay, so chapter 5 talks about atomic theory. So this is the beginning of the theory of the atom, which is talking about the model that describes the atom. So one of the ways in which chemists discuss information with other scientists and other people, they can use, well, you have the language, English, or whatever language for different countries. You have the symbols they use of the elements. You have balanced equations, you have models. And so we're going to be looking at models that communicates what scientists think about the atom. So this is called the atomic model. Atomic model. And this is a picture that represents what scientists think about in their head when they're talking about the atom. So they took the concept and the ideas they were thinking about and put it in a picture so we can understand what they're thinking about. And when they talk about the model and describe it, we can look back to this. So with the atomic model, before we get into that, let's talk about models that we relate to. When I think about models, I think about phone models. So with the phones, let me go through the iPhones, right? There were different iPhones. iPhone 1, I didn't have that. 2, 3, 4, 5. I think my first iPhone may have been a 4. So the different phone models. And so if you've had different phones, you understand there were times where back in the days they had different kinds of phone, and with times the phone got better. You had the rotatory phone where you have to kind of, you know, select the numbers in an interesting way. You have the ones where it was stuck to the wall and you had to punch the buttons. You have the corded phone where you're stuck to the wall, you can't move around. Eventually we got to cordless, and we're thinking, man, I mean, it can't get any better. You had the cordless phone, you could walk around and talk, charge the phone by putting the phone back on the hook. And then we got to cell phones. And now, even with the cell phones, we have different models of the cell phone. So the question is, why so many models? Why can't we just be happy with the first model of the phone, the one where you had to call in, call the operator, and tell the operator, I want to speak to whatever, and then she transfer you? Why do we have so many models? Can you tell me, Joy, why you think we have so many models of the phone? You can go ahead and type your answer in the chat message, chat, tape, whatever, screen. Why do you think we have so many models of the phone? Why can't we just be happy with the first one? Did anything change throughout all these years as they were making different phone models? Okay, well, since you're not saying anything, I'm going to go ahead and answer. Obviously, we have different models because the idea is the newer model does things the older model was not able to do, right? The newer model is an improvement. on the old model, right? So we're going to be seeing here, even as we discuss the models of the atom, we will have more than one model. And if you're one of those active learners like I was when I was in school, I had this question, why so many models? There was a low key reason why I was asking this question, because I was like, this is just more for me to study. Why couldn't we be happy with the first one? The newer model is always an improvement on the older model. It has more functions, probably more efficient. Now remember, the phone is tangible. These models are just drawings, right? But the drawings communicate more information and more understanding that the scientists have about the atom. Okay, so let's get into it. We'll start with the atomic model. First one I'm going to be looking at is the Dalton's atomic model based on his atomic theory. So looking at that here, we are told Dalton is a scientist and he's the one describing this model. He says, and by the way, these models are discovered through a lot of the years of experimenting by the scientists. And then they give us a summary. Instead of giving us the play-by-play, we get a summary of their work. Okay? So he said, based on the experiments he did, each element is made up of tiny indivisible particles called atoms. So he's essentially saying that elements are made up of atoms. So I'll say here, atoms make up elements. And these atoms are small and they're indivisible. They're, that's number two. They're small, they're tiny, they're individual particles, and of course they make up elements. So they're like building blocks, right? When you have a bunch of atoms, you end up with elements. Number one. Number two, he says, atoms are indivisible. They cannot be created nor destroyed. What does he mean by that? Indivisible means that it cannot be divided. That means that means there is nothing inside the atom. So we can't even go inside the atom to see what's in there because there's nothing. It's indivisible. You can't open it. You can't divide it. You can't cut it into sections. It's just like a ball, and that's all it is. Okay? Then he continues to say, all atoms of one element are identical in every aspect. So the key word here being this, every aspect. So for number three, I want to go ahead and add to that and say, Dalton is saying, say for example, he's saying all atoms of the same element are alike in every way. So what does he mean by that exactly? Because in chemistry, it's very important not just to have the knowledge, but to have the implication. Now you know this, so what? What does this mean? How does our life become different because of this knowledge? What he's trying to say is, if you were to go out there and look at the atoms of, say, helium, let's say the red circle represents helium. Then, if you see another helium atom, so this is a helium atom, the one on the right is a helium atom. And if you try to compare these two, they will have the same shape. Oops. Same shape, same size, same color, same what? Same weight. Bottom line, they're same in every way. They will be so similar that if you were looking at one, you couldn't tell you were looking at that one or the other because they're same in every way. Okay? So that explains number three. Number four, he said, atoms of one element are different from atoms of any other element. So going back to our analogy, he's saying if these are our helium atoms and they're all like each other, then let's look at different atoms. Let's say we have neon. I'm using the group 7, right? Group 8. We have neon atoms. Now, to show the difference, I've selected a different color. Say we have neon, and these are elements, atoms, neon, atoms. Once again, while these neon atoms match each other in every way, you can tell how different they are different from neon. So how can you tell they're different? Well, for one, I used a different color, right? That was on purpose. But they'll be different in size, different in color. So if you were to compare one neon versus one helium, these will be different in size, color, weight, etc., etc. Okay, so this is what he's trying to say. Based on the experiments he did, these are his results, and he's trying to communicate that to us, that hey, y'all recognize this. Yeah, they're atoms, but the atoms are different because they make up different elements that ultimately have different properties. Okay, so finally, number 5, atoms of one element combine with atoms of other elements to form chemical compounds. So here's the thing. In my other book, my other chemistry book, they mention atoms of one element combine in whole. They don't combine in fractions. When they're combining, atoms don't break apart. Remember, he said they were indivisible? They can't combine in halves because it's impossible to cut them in halves. So, in number 5, his postulate or his ideas, he says atoms combine in whole, right, with each other. Well, I shouldn't say with each other, with other atoms to form compounds. So over here, what we're seeing is different atoms combine with other atoms to form compounds. So let me see. I'm trying to think of some atoms I should pick. Let me pick sodium and chlorine. So you have sodium, usually a metal, combined with chlorine, usually a gas, and together we get sodium chloride. In the formation of sodium chloride, what we have here is, let me see. 1, 2, 3, 4. I forgot to write this properly. This is Cl2. In the actual chemical formula, it will be Na plus Cl2 to give you NaCl2. Or sorry, NaCl. So we have this, this, and this right here. Okay? So we got Na and Cl2. In the actual product it forms, though, you have 1 Na for every Cl to form sodium chloride. Remember, sodium is a metal. Chlorine is a gas. When they combine, they form a salt. Okay? And this is what we call table salt. So down the road, we'll be looking at different kinds of salt, and then we'll learn that we can't eat all those salts. The only salt that we tend to eat, sodium chloride. Sometimes some people eat potassium chloride, but the most common salt we eat is table salt, sodium chloride. Okay. So the other thing that he was trying to communicate, Dalton, back to him, is that when you're forming a new compound, what is really happening is the atoms are not changing the identity, but they're just combining differently. Okay? They're breaking up with the atoms next to them and then forming bonds with new atoms. You can see here on the left, for the sodium, you have 4 sodium atoms combined together. On the right, you have chlorine atoms combined together. The chlorine breaks up with the chlorine, the neighboring chlorine, to form a bond with the sodium. That's how we get table salt, sodium. Okay? As the sodium combines with the chlorine. So moving on, Dalton was right in certain ways, and then he was wrong in certain ways. One of the ways we cheer Dalton, like after him doing all this work, presenting his work to the masses, his work led to other work. So I'm going to say right here, the success of Dalton. What did Dalton do well? For one, we didn't really have an atomic theory until Dalton came around. So he was one of the main people who came up with the first atomic theory, right? And then his ideas led to other ideas. First thing, the law of multiple proportion. This law helps us to understand the components of the elements inside the compound. Scientists, it may have taken scientists longer to figure out this law, but scientists were able to think this way because of Dalton. Dalton's ideas and the way he was able to come up with theories about the atom helped other scientists come up with this idea here. It would be like if there was a fashion, right? Say, I heard recently tie-dye came back. Okay. Now, I've lived long enough for tie-dye to come back. Because back in the days, tie-dye was a thing as far as style was concerned. Tie-dye was a style. It came, and people decided, oh, we want to make different clothes with tie-dye. So they came up and then designed different styles with tie-dye. So now you have not only one person designing a style with tie-dye, you have a bunch of different people coming up with inspiration. So one person is an inspiration for others. And so here we're seeing that Dalton is inspiring other people into doing different work. Okay. So once again, his work inspired others. Okay, first thing, law of multiple proportion. Number two, we'll see law of definite composition, and then law of conservation of mass. Okay, so these three laws were inspired by Dalton. His work led to other scientists being able to come up with these three laws. Okay, so it's important when you get to this section to make sure you know these laws. So what I'm going to do is I'm actually going to start with number 3, go to number 2, and then go to number 1. I'm going to kind of go in reverse. Okay, I just realized I got left alone. I don't know what happened. Okay, so over here, let me start with the law of conservation of mass. The context of this law, or this law works when you're looking at a balanced equation. So the context here is the balanced equation. And the idea is, if you have a balanced equation and you look at the beginning of the equation and compare it to the end, the reaction, and compare it to the product, then you notice that mass is being conserved. Okay, that was kind of weird. I wonder what happened there. Yeah, mass is being conserved. So what this means is, in a balanced equation, the total mass of reactants equal total mass of products. Okay? If you were to write this as a bottom line, mass reactants equal mass products. Scientists wouldn't have come up with this idea once again without the inspiration for Dalton. So we're saying, Dalton, good job. Thanks to you, we now understand this. Okay? So you want to go ahead once again as you're studying, going over your homework, that you understand this concept. So I said I was working backwards, right? So this one, I'll go through that. That will be number one. Now I'm going to go through number two, law of definite proportion or definite composition. In this law, the law of definite composition, this law has a context. And what is the context? The context is components of a compound. So when you're trying to look at a compound, you're trying to figure out, well, what elements are in the compound and what law helps me to know that this compound is what I think it is, the law of definite proportion comes into play. For example, okay, if I were to tell you right now, go find a glass of hydrogen peroxide and then find a glass of water, they look the same. They really look the same. Hydrogen peroxide visually looks like water, right? So if somebody has a glass of hydrogen peroxide and a glass of water, they look alike. But how can you chemically tell one is not the other or one is different from the other? How can you tell? Well, you will look at the components. What is inside the compound? It will be like the ingredient of the compound. You will look at that. And when you look at that, you will see here that in this formula of H2O2, you have two hydrogens and you have two oxygens. On the other side, versus in the water formula, you have two hydrogens and one oxygen. Okay? So here you have two hydrogen for every two oxygen, and then over on the right side you have two hydrogen for every oxygen, right? So based on this, we can tell these are different. And then we're told later on, if you look at the masses also tell you these are different. Let me show you here how you can tell. You can figure out the mass of hydrogen and compare it with the mass of oxygen in the formula of H2O2. So in H2O2, the mass of hydrogen, I look at my periodic table to get this number. In my periodic table here, let me see what I have. 1.008 gram, right? But it shows that I have two. So times 2, I end up with 2.016 gram. And then the mass of of oxygen in the same formula. For oxygen, I have 16.000 grams times 2. Oh, no, sorry. Yeah, times 2 here I have, hold on, let me get my calculator. 16, I rounded it up a little bit. 16 times 2, I have 32. Let me verify that. Yep, 32. So, in the formula, in H2O2, there is 2.0 grams of H for 32 grams of oxygen. And if you want, you can simplify this even further and say divide by 2, divide by 2, and you can say you have 1 gram of hydrogen for every 16 grams of oxygen. And this relationship here is what we use to verify, to prove. If you were asked to prove the chemical is hydrogen peroxide, if you can figure out the grams of hydrogen and compare it to the grams of oxygen, then you can prove liquid is hydrogen peroxide. So this one here, this relationship is used as a proof. Okay? Same thing with H2O. With H2O this time, though, we're looking at the mass of hydrogen, which is 1.008 grams, versus the mass of oxygen. So before I forget, let me double the mass of hydrogen because it is two hydrogens in the water, right? So if this is two hydrogens, this would be what? 2.016 grams. And then compare this with the mass of oxygen, which is going to be 16.000 grams. Now what we have here, comparing the two, in H2O, there is 2 grams of hydrogen for 16 grams of oxygen. Divide by 2, divide by 2, we have 1 gram of hydrogen for 8 grams of oxygen. So this relationship here is the relationship that's used as proof for H2O. So notice we're only using the masses as proof. Okay? So they call this the mass relationship. The mass relationship is used as a proof for the water versus the hydrogen peroxide. So here's the thing. I went to the airport one time, and then I had a water bottle. You know how they say do not bring water to the airport because it could be a weapon, right? Not the water itself, but a chemical that looks just like water, but it's a different chemical, like an acid or anything like that. So I didn't know they don't allow peroxide. I didn't know. And I tend to carry peroxide just in case you have cuts, or sometimes to rinse my mouth, you know? So anyway, I wasn't aware of that. And well, I had water though. This wasn't peroxide, it was water in my water bottle. We go through security, get to London, as I'm going home. And in London, they're like, oh, I see you have a bottle. They pass the bottle through the security. They pass it through this machine. They do all these chemical tests on it. And then when I'm done, they say, okay, here's your bottle. Stand there and drink it. I'm like, but y'all did the test already. Didn't you get that this is just water? Didn't you see the proof? It's just 1 gram of hydrogen for every 8 grams of oxygen. Isn't that enough for you? They're like, no. You were not supposed to bring this water through security. Stand over there and drink it. So I stood there and I drank the whole bottle. I mean, I'm talking about 32 ounces of water. Yeah. Ever since that happened, now I don't play. When I get to the airport, I'm like, when I get to the airport, I don't even take water into the airport. I just empty it out. Even between one airport to the other, like I don't mess. After one time, I'm like, never again. Okay? So finally, after we're done with this law of definite proportion, so I call this law, I paraphrase it and I call it the law of definite ingredients in the compound, right? Because this law is saying if you have water, regardless of who made that water or what the water source is, you will always have 2 hydrogens for every 1 oxygen, okay? And that's essentially the paraphrase of this law. Next thing is law of multiple proportion, which states that when you have more than one compound, right, then, well, this one here is a little hard to explain without looking at their what they said. So let me go ahead and read what they're saying. But when you have 2 elements that combine to form more than one compound, so it says here, when 2 elements combine to form one compound, this is a law, by the way, the different masses of one element that combine with the same mass of the other element are in a simple whole number relationship. So what this is saying is, let's say we have 2 elements, and these 2 elements have an ability, and their ability is to combine to form a compound, okay? So in the example they gave us here, the 2 elements are carbon and oxygen. So you have carbon and oxygen, two elements combining to form more than one compound. Our first compound here, you can see on the left, carbon monoxide. Second compound on the right is carbon dioxide. If these two elements combine to form two different compounds, carbon monoxide and carbon dioxide, then different masses of one element, you can see in the first formula, you have one compound for one carbon for one oxygen. In the second one, you have one carbon for two oxygens. So the amount that's changing from A to B from this first situation to the second situation is the amount of oxygen, not the carbon. The carbon amount is remaining the same. So when it says here, the different masses of, I'll say, oxygen that combine with the same mass of carbon are in a simple ratio of whole numbers. Okay, so I'm going to tell you this. If you look at these two, right, can you look at the relationship between the first oxygen and the second oxygen? The obvious relationship is the second compound has twice the number of oxygen. You can see them visually, right, from here to here. It's 2 times the number of oxygen, but the same amount of carbon. This is the whole number relationship they're talking about. That there is a relationship that relates the two different compounds that have the same starting elements. Okay? So just to kind of illustrate that further, say you had CO versus CO3. You can see here the number of carbons don't change, but the number of oxygens change. By how much? By 3. So in this case, the law of multiple proportion will show us from the first equation to the second, we have 3 times the number of oxygen, right? What we just saw right now, CO to CO2, we have 2 times the number of oxygen, okay? So twice the number of oxygen, and then here we have 3 times the number of oxygen, okay? Okay, so that's pretty much the law. It's really not as bad as it seems. So here's a picture showing us the illustration. It's using a picture to illustrate what Dalton said. Remember, Dalton said that elements of the same compound pretty much have the same type of atoms. So you see here, same type of atoms. None of these are different from each other. Same over and over again. Okay? Then he said, you cannot destroy the atom or create it. He said, you can't even break apart the atom to figure out what's inside. And then he also said, atoms of the same element have the same weight. But if you compare atoms of different elements, one is going to be heavier than the other. In other words, he's trying to say, if the atoms are different or they have different weights, they got to be from different elements. That's all he's saying. And then over here, he also said, atoms of different elements may combine in a ratio of small whole numbers to form compounds, right? And remember, this is what led to the law of multiple proportions. It's all about Dalton. Okay. Now, after we have praised him and said, oh, Dalton, you're so great. Because of you, you inspired other scientists to come up with these 3 new laws. Now we criticize him. Okay. So this right here is the criticisms. Now I can't spell criticism. Okay, anyway, the point is that this is what he didn't do so well, right? All of a sudden I'm looking at this, I'm like, how do you spell this word again? Anyway, this is where Dalton fell short. Number 1, in defense of Dalton, like imagine you, as you're learning this, when I was learning this, I was so bored out of my mind in college. In high school. Well, more like in high school. By the time I got to college, I said, you know what? What if I was a lawyer and I was hired to defend Dalton the man, the scientist? How will I tell the masses, hey, don't blame him. He did the best he could. And so I like to teach it from that point of view. Imagine you were defending him. He did well, right? He did the best he could. Why did he struggle to see electrons and everything else we're going to talk about? Here are the limitations and the challenges that Dalton faced. Limitations. Technology. In his time, technology was very archaic. He didn't have enough equipment to find what the others found. And time was passing and new technology was coming up and more research work, and therefore there was more information out there for the others to study. Old technology was the first limitation. The other one was there wasn't a lot of information published about atoms, so there was also less information to gather from. Okay, so time has passed, technology has gotten better, people have gotten more information about the atom, and then we fast forward to a scientist called J.J. Thomson. I like to call J.J. Thomson J.J. like I know him. Okay, I don't really know him, but talking about him a lot, I'm getting the feeling that I know him. J.J. Thomson is the scientist who is given credit for discovering the electron. The electron by J.J. Thomson. So he was doing a lot of work. It's funny that they spell it with a P here. I would spell it with just no P. Anyway, he was doing a lot of work and he discovered that there were electrons inside the atom. How did he discover this? Oh, okay, I guess, let me see. Oh, a time had come in the world of science where scientists were taking elements, compounds, whatever it was, and then they were making it into vapor and passing electricity through it. Long story short, J.J. Thomson discovered the existence of electron. So not only did he discover that, he actually went out and released his own model of the atom. So one thing I haven't done yet here before I got to JJ is I haven't drawn a picture of Dalton's model. Let me go ahead and bring in a picture here and draw what Dalton's model will look like. Okay, so except for one group of scientists, all the scientists agreed the shape of the model of the atom was round. So this is Dalton. He says his atomic model, round. That's it. That's pretty much it. It's round. You ask him what's inside? Nothing. So this is Dalton's atomic model. And then J.J. Thomson comes in later on and he discovered the electron with his experiments. And he realized the electron was spread throughout the interior of the atom. So it looks like this, and we'll call this J.J. Thomson's model of the atom. He calls this a plum pudding model. Now, in America, it's hard to really understand the plum pudding. What is a plum pudding? So, of course, we got Google. So I went ahead and Googled, and plum pudding looks more like, I would think a pudding would be soft. It looks more like a muffin. So imagine a muffin that came out round, like a donut hole. So it's round, but it's really a muffin. And inside the muffin, or like a blueberry muffin that's round, inside the muffin, you would have blueberries, right? So in J.J. Thomson's model, plum pudding model, inside the atom, you have, I was about to say blueberries. No, you don't have blueberries in the atom. You have electrons, the electrons that he discovered. And then the core of the atom was just positive charge. And then you have electrons inside the atom like you'd have blueberry inside a muffin. Can you imagine? You're going down in history and that's your contribution to science. But he apparently likes plum pudding so much, he names his model Plum Pudding. Okay? So you see the improvement, right? In the first one, we have a circle. We all agree it's a circle. Dalton did well. It's a circle. But he was wrong in that he said there's nothing inside. JJ comes in and says, oh, there is stuff inside the atom. From his experiment, he found there are electrons, and the electrons are spread out throughout the interior of the atom as though you had blueberries inside a muffin. Okay? So hopefully you can see the progression. The electron is negative charge. So remember, these are all negative. This is negative, 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 negative. He also found out that the electron has a very, very small mass. Okay, so here the electron is almost massless, meaning it's not very heavy. It's kind of almost like it's not even there, but we know it's there. Okay, and then he gave the symbol of the electron E minus. So make sure you know this. The person who gets credit for the electron is J.J. Thomson. Okay, I like to call him J.J. Okay, so once again, plum pudding model. This is a model of the atom proposed before the discovery of the nucleus. So they hadn't discovered nucleus yet. And we're going down through history, right? I remember a student asked me, well, why do we even learn the history? Because it's this in chemistry, everything builds up on everything. We wouldn't have discovered the new one if we didn't know the old one. And the new one only makes sense if you know the old one and how it worked, right? So I told here the jello has, the jello is the interior of the model, has a positive charge equal to the negative charge contributed by the electrons, which are modeled wait, what? Oh, as the grains of sand. Yeah, this is just describing the model of the atom, right? And I already discussed that. Then we move on and look at this experiment. Rutherford, sometimes called Rutherford. I don't really know how to pronounce this because it's German and I'm not German, so I just call it Rutherford. I'm pronouncing it the African way, okay? Rutherford. So Rutherford is actually a student and a friend of JJ, okay? Before we get into the chemistry, we need to know the story behind. There are times where I wish the textbook have the drama of the things that were going on behind the scenes. Dalton wasn't really the friend of JJ. JJ came way later. Then we have JJ Thomson. But JJ Thomson is working with his student, Rutherford. His student and his friend, okay? As JJ Thomson publishes his model, his friend Rutherford is like, okay, you know what? I want to help my friend and my mentor, JJ, to prove his model. I am going to do an experiment, and this experiment for real will help to solidify J.J. Thomson's model, and the whole world will really accept his model. Because some people are like, we're not so sure about this model, okay? So he does this experiment called the scattering experiment, the gold leaf scattering experiment. He takes a piece of foil, not aluminum foil, it's a gold foil, but it looks like an aluminum foil, a very, very, very tiny piece. And then he passes a source of, it says here, fast moving alpha particles. All you need to know here is these particles were positive charged. So he was thinking, if my friend JJ is correct, then these positive beams, as they travel through the gold leaf, by the way, remember the gold leaf is very thin and very tiny. If you look at the cross section, this part is very important. The cross section of the gold leaf, he picked a leaf, a foil, also called leaf, that was so thin, it was like one layer of atoms thick. So he said, if I pass the positive beam through it, most of it will just go through if JJ is correct, right? Most of the beams will go through. Why? Because the interior of the atom is full of negative electrons. They won't really interfere with the beam. Most of the beams will go through. This is what he expected. No interference. The beams go through. I've proven my friend right, and our friendship continues, right? Well, what happened? Okay. What happened is, in a way, he was right. Most of it went through. So you see these ones here? Most of it went through. But there were some beams that bounced back, like this one here. And then not only did they bounce back, they only bounce back when they seem to hit the core, the center, like the bull's eye in the atom. So now he's like, oh snap. Well, he didn't say oh snap. I'm just trying to dramatize it. I gotta talk to JJ. So I don't know the conversation. I wasn't even born, but I like to dramatize things. So I'm trying to imagine Rutherford, right, trying to talk to JJ. He's at his door. JJ, we need to talk. JJ's like, yeah, come in. What's up? What's going on? So like, okay, right. What had happened was, sorry, this is just me trying to, what had happened was I was trying to help you prove your model, but my experiment shows your model is wrong. It's like, wait, what? Your model is wrong because if your model was right, all the beams should have gone through. Your model is wrong because in your model, you didn't say there was something hard in the center of the atom. Obviously, there's something hard in the center of the atom that's causing this beam to bounce back or to deflect. You didn't say anything about that. Okay? Once again, history doesn't tell us what happened between the two. All I know is, okay, all I know for sure, his friend, Rutherford, who was supposed to be JJ's friend, all of a sudden he's coming out with his no, his own model. Okay? When my mind goes in this, it would be like there was a group of singers, and somehow the group breaks apart and then one person in the group releases a single. This is where my mind is going. Like Rutherford, all of a sudden, he's coming out with his own model. I'm like, wait a minute, Rutherford, wasn't your job to help your friend out? Weren't you trying to help JJ? He comes up with his own model, the nuclear model of the atom. In the nuclear model of the atom, now he's saying, as the name communicates, there is a nucleus. Up until this point, scientists never knew there was a nucleus. According to Rutherford's experiment, he finds out there is a nucleus. So most of his discovery and his discussion is all about the nucleus. He says every atom contains an extremely small, extremely dense nucleus. And then he says all of the positive charge and nearly all of the mass of the atom are concentrated in that nucleus. That nucleus is positive. But that nucleus is small, but it's also very, very hard. So much so that as I passed those beams through the atoms, the beams which were moving very fast, and by the way, those beams are heavy. They're atoms, but they're heavy. As they were going to the core of the atoms, they were being hit hard and deflected. So he's saying, yeah, it's small, but it's also very dense. And then he's saying the tiny nucleus is surrounded by a much larger volume of nearly empty space that makes up the majority of the volume of the atom. He's saying even though the nucleus is in the middle, the majority of the atom is technically empty space. And in that empty space is where you will find your electrons. And he says here, the electrons, they're there, but they're very thinly populated. That's why the electrons were not able to stop the beam of particles passing through. Okay? He agrees, yes, the total charge of the atom is neutral because they neutralize each other. So, you can see it right here. This is a picture of the nuclear model of the atom, Rutherford's model, right? Remember, the goal of Rutherford was to help his friend. Now I call Rutherford JJ's ex-best friend. They may have still been friends, but I don't think they were best friends anymore. I mean, I find it hard to see a relationship survive this. How you go release your own model when your goal was to come and help me with my model, right? But you know what? Things we do in science are not personal. You can't take it personal. So I don't know. Once again, if I could go back in history, I like to go back and see what happened between these two men. Did they remain friends? I don't know. Okay. So here is a Rutherford's model. You can see right there you have a nucleus, and then he's saying this whole huge empty space inside the atom is occupied by the electrons. And so here we have the nucleus. Yeah. So let's go ahead and do a quick review before we go into the rest of the stuff here. Let's see how many models we have right now. Now we have 3 models, right? As you can see, each model is telling a different story. Not completely different, but each model is getting deeper, right? So let's go with Dalton's atomic model. Dalton's the first one. Dalton, he just said the atom is round. Then comes JJ, okay? And he said, yeah, the atom is round, but there is more to the atom. This side has negative electrons. And the core itself is positive, like that. Then Rutherford, who is JJ's ex-best friend, in my mind, he comes in and he's like, oh, no, no, no. Here's what's happening. There is a nucleus in the middle, and the nucleus is positive. Then around the nucleus, you have the electrons, okay? So Dalton's model doesn't have another name. It's just called Dalton's model. JJ's model, of course, is the plum pudding model, plum pudding. And then Rutherford's model is called the nuclear model, named after the part he discovered, nuclear model, okay? So this is the oldest model. I shouldn't say the oldest, but this is the oldest that we discussed. The ones that we discussed, this is the oldest. And of these three, right now, this is the newest. Now we have two more models to discuss. We have the most popular model, the one from Bohr. You know, if you've watched Jimmy Neutron or if you've watched Big Bang Theory, that's the one that Hollywood likes, Bohr's model, right? That's the one that, you know, if they have some kind of science movie, they show Bohr's model. None of these models make it in the science movies. And then the last and the newest model is quantum mechanical model, and that one does not make it in most movies. If the quantum mechanical model shows up anywhere at all, it's in some sci-fi high-level science movie, okay? Because the quantum mechanical model, even the name is not very, it's not very friendly. I mean, quantum mechanical model. It looks so theoretical, right? People can't really relate to that. But the Bohr's model, they like that, okay? Okay. So this is telling you the reason why, you know, the rift between the two men, JJ and Rutherford. Why did we even get the nuclear model? Because according to JJ, most of the alpha particles were not deflected, okay? He was thinking maybe more will be deflected, but they were not, because remember, the electrons are very small. Electrons are small and light. They were not heavy enough to deflect. So when I was learning this, I was thinking about it like this, right? I knew not bowling. What's the other thing where you use a ball to hit another ball? What game is that? You need to help me. I can't remember it right now. What is it? Pool. I wanted to say billiard or snookers. It's the same thing. Where I come from, that's what they call it. Anyway, pool, right? In pool, you throw one ball at the other ball, and then the one that's stationary deflects the ball once the other ball hits it. You know, this ball is moving this way, and then bam. So the issue with the experiment here is the alpha particle, when it runs through the electron is so tiny and so tiny. So it was not able to deflect this. So this thing just went by undeflected. But on the other hand, when it encountered the nucleus now, even though it wasn't very big, it was dense. When this encountered the nucleus, right? And this right here is the nucleus. Now the nucleus fought back, okay? Electron is small. It's not dense. It could not fight back or deflect the particles. But the nucleus, no, it bounced back. So the alpha particle was deflected. That's how they knew the nucleus was in the middle. Particles near the nucleus are either repelled by positive electrostatic forces. In other words, because this is positive and the nucleus is positive, even the ones that didn't actually bump into the nucleus, they were deflected. Why? Because like charges repel each other. So we see very few particles that are on the collision course with the nucleus were repelled backwards. So none of them went completely backwards like this, but many of them were kind of repelled on the side, okay? Once again, this proves the nucleus is positive. It proves the nucleus is in the middle. It also proves the nucleus is dense. So his experiment proves three things at least we know about the nucleus. Three things about the nucleus. Number one, I should say maybe four things. Nucleus is positively charged. Number two, it's dense. Number three, it's in the core or the center. I should say center is a better word. The nucleus is in the center of atom. And then, since the electron was very, very light, we learned the fourth thing, which is the mass of nucleus, essentially the mass of the atom. That was a lot of information that scientists learned. They didn't know this before. They didn't know that. Through the experiment, they learned all this information. Okay? So by showing you all of this, weren't we trying to tell Dalton what he hadn't done well? So going back to the picture, remember Dalton said there was nothing inside? This experiment and this experiment are proving Dalton wrong. How? By saying there are subatomic particles. And what are these? I'm not done yet, but we can see that we have electrons, and electrons were discovered by J.J. Thomson. B, protons, and we'll see in a little bit that it was Rutherford who discovered protons. And then finally, Rutherford's student that his story hasn't been told yet, he discovered the neutrons. His name is Chadwick. So these three men together help us discover that subatomic particles exist inside the atom, which is the opposite of what Dalton said. So the proof and the existence of subatomic particles essentially told Dalton, you got it wrong. There are particles inside the atom. There are three of them: electrons, protons, and neutrons. Okay, so let's go ahead. The story. Okay, yeah, so like I mentioned, proton carries a positive charge. It is found in the nucleus. It was discovered by Rutherford. The symbol for proton is positive. And then, of course, you finally have the neutron. So, JJ, oops, how do I write JJ like that? JJ, he has a student, Rutherford. Who has a student? Chadwick. And Chadwick, eventually he's trying to measure the mass of the atom, right? So I want you to understand the struggle, right? The struggle in chemistry. It's a real struggle. You're trying to learn this information, but some things don't make sense and they don't compute. He noticed, he's trying to figure out the mass of the atom. That was his main job. And before Chadwick discovered the neutron, scientists were under the impression that the mass of the atom is equal to the mass of the positive charge. In other words, the mass of the atom is the mass of the proton. Now, Chadwick started doing experiments and he realized, the mass of the proton is actually smaller than the mass of the whole atom. There is another mass that nobody is accounting for. So long story short, they discovered that there was something else inside the nucleus that had no charge, and guess what that was? That was the neutron. And the neutron was the electrically neutral subatomic particle within the nucleus. And the neutron was the one that was missing, the missing part of the nucleus. Therefore, the mass of the atom is mass of proton plus mass of neutron. You cannot forget the neutron. So in the end, they conclude the mass of the atom is mass of proton, mass of neutron. Okay. Remember, the neutron was discovered by James Chadwick. we see here the mass of proton is almost equal to the mass of the neutron. Okay? So, you know how I like to tell stories. I mean, how else will you survive this stuff, right? You can survive it without the stories. I just like the stories, plus the chemistry. So, I'm teaching this on campus, right? And then I say, okay, well, so now we conclude the mass of the atom equal mass of proton plus mass of neutron, right? And then I said, but don't forget, the atom has a nucleus that's proton plus neutron, and it has electrons. So my one student says, this is on campus, and this is years ago, plus mass of electron, right? To get the mass of the whole atom. Like take the parts, add them together to get the whole. And I told her, well, we don't include the mass of the electron. She said, what? I said, yeah. When it comes to the mass of the atom, even though electrons are present, we only use the mass of the proton and the mass of the neutron. She's like, no way. Why? I said, well, when you look at the actual mass of the proton and the neutron and you add them, even if you add them to the mass of the electron and then you round up, you find out that the mass of his electron is too small to be significant. You end up rounding it off. So the mass of the electron is too small to be significant. So it's just easier to leave it off. She confronts me, not in a rude way, but she's like, it's like saying the vote of one person does not count. I said, I need a moment to think about that. I'm like, I don't think I've ever had anybody take this so personal or just be so deep about this. This is so deep. And I said, so I have to try to save face, right? Because I'm like, I didn't make up the rules, but I'm the one presenting the information. I told her, would it make you feel better if you knew that we make it up to the electron? Because in the end, even though the electron doesn't contribute much when it comes to the mass, it contributes the behavior of the atom and so many other things. And then we talk a lot about the electron more than the neutron and the proton. Does that make you feel better? She said, I guess. And then she left. I'm thinking, oh, snap. She's not coming back again to this class. She's already upset. She came back. She had a really great attitude. So I was like, okay, great. Woo! Yeah. But was I upset? Someone looked at me like, why? I'm like, no, I wasn't upset about that. She had to be paying attention to recognize what I said. So I'm like, hey, like I said, the electron has a negative charge. Its mass is very small compared to the mass of the proton. Symbol negative E, discovered by J.J. Thomson. Okay, once we've done all that, now we are moving on. There is one other experiment that shows that Dalton is wrong. Once again, this is not a bash Dalton's day. No, it's just that we need to figure out where things went wrong, right? To resolve it with the information we have right now. As time went by, once again, technology improved, and then there was more information. So it's very important for quality information to be published, right? So with more information, like more scientific knowledge, scientists are beginning to ask questions. I mean, in the beginning, they're always asking questions. When I was a kid, I would ask questions all the time. If I was told something, I'm asking why, why. I never just took information for what it was. I'm always like, I want to know more. Why? What's the logic, right? Scientists discovered isotopes. Okay, so let me give you guys the bottom line here. The discovery, oops, now I can't spell. The discovery of isotopes proved Dalton's postulate. The postulate is it's like a summary, right? It's like a statement, but it's more than just a statement. But it proved one of his summaries or his that he made wrong. Okay? So first of all, we need to ask ourselves, what is an isotope? An isotope is elements with atoms of different masses. Okay? It means you have the atoms of the same element, but one is heavier than the other. Remember back then, Dalton said, if they have different masses, they come from different elements. We're being told here that it's the same atom, right? Let's say we're looking at sodium. They're both sodium, but one is heavier, and then the other atom is lighter. It's not much heavier, but it is significantly heavier for scientists to notice. Oh, if only I can spell. So it's like, wait a minute. Didn't Dalton say, though, that if one was heavier, if one atom was heavier and the other atom was lighter, then that means they came from different elements? Yeah, they agreed. But then we're seeing right now we have two different atoms. I mean, they're the same, they look the same, but when you weigh them, one is lighter, the other one is heavier, slightly. But they're both sodium. They both behave the same way in every other way except for their weights. Now what? Okay. So now to go and publish it, right? So once scientists discovered the isotope, they proved Dalton wrong. Dalton said, if atoms come from the same source, they are alike in every way. Future work showed that that's not true. So now we're going to be looking at what isotopes are in more details. To understand isotope or to even recognize it, how can we tell the formula they gave us is an isotope? We will look at something called the symbol. So in the chemical symbol, you have atomic number. Atomic number is a number that tells you the number of protons. Remember the positive charge in the nucleus? Yep, that's it. In the atom of an element. And then we're told total contributions to the mass from the protons and electrons is the same for every atom of the element. Okay? But what are isotopes? Isotopes are two or more atoms of the same element that have different masses. So you would think they're the same, but they have different masses. So the question is why? What makes the masses different? Up here, we're told the number of protons is same, number of electrons is same. So the part of the atom that's different is the number of neutrons. Okay, the particle, the subatomic particle that has no charge, that's the part that's neutral, and that's the part that's different. So we're told here we can identify isotope by its mass number. Mass identifies isotope. So what do I mean by that? Okay, as we read this here, I'm trying to make sense of what they're saying. What they're saying is this. Because most of the time, I'm just going to write here, we identify, as students and teachers, isotopes from the isotopic symbol. How is the symbol written? Most of the time, I'll show you how the symbol is written. For example right here, these are isotopes of carbon. So they write the symbol. This is the format. The symbol dash mass of atom. Okay? And the mass of atom is also called atomic mass. So symbol dash atomic mass. So remember the statement that says we use the mass to identify the symbol of the isotope? Yeah. So I'm going to show you symbols of carbon isotope or isotopes of carbon, right? The carbon symbol for the periodic table is C. So I have 3 C's because I'm going to be showing you 3 isotope symbols. One of the isotopes has a mass of 12. The other one has a mass of 13. The other one has a mass of 14. Okay? So if you were to weigh a large amount, which is called a mole, if you were to weigh in the lab, we tend to weigh molar amounts. So if you were to weigh, let's say here, 1 mole of each isotope in the lab for carbon 12 in a container, you will get 12 grams for 1 mole. For carbon 13, also in a container, you will get 13 grams. For the same amount, for carbon 14 in a container, same amount, you will get 14 grams. And the amount I wrote here is 1 mole. I'll discuss 1 mole down the road. But the idea here is, you can see, right, this is heavier than that. This is heavier than that. So as we go from left to right, we have different weights. But are all 3 carbon? Yeah. How do I know that? The symbol says carbon, carbon, carbon. Heavy carbon, light carbon. Okay? So the existence of the same element with different weights is called isotopes. So these 3 are isotopes of each other. Okay? Scientists have this knack, especially chemists. When they discover something new, they gotta name it. You gotta name it. How else will you describe it? You know? We have African scientists, but we don't bring our Africanism into the science because I guess there's a universal language for science, and Africans can make up their own science, right? But I grew up in Tanzania, and in Tanzania, the language, not just in Tanzania, but most languages outside of, let me just talk about African languages, the one I know. Most African languages are descriptive. Instead of having one word like isotope, and then it has this long meaning, we have like a lot of words, and then we don't have one word. So we have like the color maroon is called old people's blood. Why? I don't know. The color brown is like poop. I don't know. But in the world of science, when something new is discovered, it's like this whole paragraph, and they come up with one term, and the one term describes a whole, paragraph. So this is very non-African, right? If it was an African, there'll be a whole paragraph to describe what an isotope is, and there will not be one word in the place of that paragraph. Here we have one word. Isotope stands for elements having having atoms from the same element, and they happen to weigh different amounts when they're weighed. Okay? So now that we've seen that, remember the mass of the isotope identifies them. Now we want to know, though, how many different ways can this isotope be written? I already showed you one way. This is the format like that, the symbol and the atomic mass. There is another way. In the other way, it has both atomic number Z and mass number A. So it looks like this. Okay? You have your electron symbol, and then you have A and Z. So this right here will be the element symbol or the formula, right? A will be the mass number, and then Z will be the proton. By the way, the periodic table is written using this format right here. Okay? So now we need to know what the components of this are. We're told here the mass number is the total number of protons and neutrons in the nucleus of the atom. So I'm going to go ahead and break that down in order. Let me show you a new page, and then we'll look at our isotopes. So we have X, we have A, we have Z. So Z is the atomic number. Make sure you have all these different names, right? atomic number, also known as number of protons. So inside the atom, in the nucleus, you have proton plus neutrons. Outside, you have electrons, right? Then over here, A, that is the mass number, or number of protons plus number of neutrons. Okay, so disclaimer. Please note that your periodic table is usually written like this, right? Sometimes it's written like this. You have your up and down, like A and Z. Well, it's written in the symbolic form. Here's the thing. Do you want to memorize this order? No, you don't want to memorize this order. Why? Because sometimes they switch this around. So what I do memorize is the magnitude of the size. Atomic number is only made up of one subatomic particles, so it tends to be smaller. This other one, the mass, has got atomic number and number of neutrons. So this tends to be larger. Okay? So here's the thing. The atomic number, because it's constant all the time, this is used to identify the element. Like earlier, I was telling you about the mass relationship to identify the element, like the whole water thing, the compound. Now the atomic number is used to identify the element. It would be like a social, right? The social is many numbers. Atomic number is one number. Only one number, atomic number, number of protons, belongs to one element, like a social security number, right? So atomic number 1 belongs to hydrogen all the time, every day. Atomic number, let me look for my favorite element, 98 belongs to California. Not because I necessarily like California, but I like the beach and one thing leads to another. So yeah, atomic number 98 belongs to California all the time, any day. Okay, so the atomic number is used as an identifier. It's also equal to number of protons. Okay, so number of protons used to identify element, like fingerprints, like social security number. But electrons, we'll see down the road, used to determine behavior of elements. Okay, so please make sure you know these important points. Okay, let me see where I'm at. Yeah, so here they're showing you once again name of isotope. It shows you how they name it here. So let's go ahead and look at, I already described this. I want to go ahead and work on this part here. Example, what are the nuclear symbols? So this is nuclear symbol, or sometimes called isotopic symbol, for carbon-12 and carbon-13. So remember that I told you guys the number of protons never change. So you can go ahead, when you write carbon-12 and carbon-13, remember that there's 3 parts to this formula. You have the symbol, you have the mass number, then you have the number of protons. Use the periodic table to find that missing number, the number of protons. Remember that number will be the same for the same elements. And these are both carbon. I look at carbon and I see number 6. This would be 6 and this would be 6, right? That number is also the identifying number, like the social, for carbon. There's so many numbers like that. There's so many formulas, numbers, symbols, pictures that are used like socials or fingerprints to identify elements. Okay? Science is always trying to figure out who done it. So it's important for them to know, how can I prove without a shadow of a doubt this is carbon? Look at this atomic number, right? Yeah. So let me see. Oh, this one here. I'm trying to look at the time. Okay. So I guess I'll get to, yeah, I'll get to this slide and then I'll be done. So let me go through this one here first. So this is saying, fill in the blanks in the following table using the relationship A equals Z plus N. So A is the mass number, and then Z is number, I guess I'll say proton number, and then N is the neutron number, right? Neutron number. So before we go into this, certain rules that we have to know. Number of protons equal number of electrons when the atom is neutral. So let me see. Ooh. I can write this on. Let me move this to the left. Okay. So protons equal electrons when you have a neutral atom. Okay. So let's go ahead and look at this. Name of the element: barium, oxygen. These ones here, oh, this one here, I guess this would be zinc. Okay, I don't know what this one is yet, but you know what? I can use the atomic number to find out what it is. What is 82? Okay, let me see. Pull this up, periodic table, 82. Where is 82? 82. Ooh, lead. PB. 82. So I use my atomic number to figure out what, oh, sorry, my bad. You know, this is the issue with enthusiasm. I'm too enthusiastic. This is lead. My bad. I need to follow the order, right? They said name, not symbol. Symbol, PB. Now I'm doing this right. Zinc, symbol, ZN. Oxygen, symbol, O. Barium, symbol, Ba. Okay? Atomic number, I have to go to the periodic table and figure out what the atomic numbers are. Barium is what, 56? I'm looking at the smaller of the two numbers in my periodic table, okay? So let me see if I can find this real quick. Let me navigate out here. With the internet, you never know, right? Let me look at this periodic table. Can I get an image? A good one? Sometimes the periodic table is just like you're going around in circles. Can I zoom in on this? Command plus 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 plus. Okay. Okay. So the words got bigger than the symbol. That's okay. Barium is right here. So y'all can see I'm copying this out. 56, right? Okay. And then oxygen is right here. And this is 8. Right? Because it says it's 3, 4, 5, 6, 7, 8. Yeah. And then lead, it's like 80, 81, 82. What did I say for oxygen? Oxygen is 8. Oh, I wrote in the wrong place. That is 82. Zinc, is that 30? This is 30. Oops, wrong thing. Okay. So we can see, I'm looking at the small number. This is 30. For barium, 56. For oxygen, 8. For lead, oh, I already have it though, but if I'm looking for it, it's right here, 82. And then for zinc, it's 30. Okay. I don't think I need anything else here. I'm done with this. What did I do? Oh, there, here. And then over here, let's see. Number of protons equal atomic number. So 56, 8, 82, 30. Number of neutrons. Number of neutrons, you have to take the mass number and subtract number of protons. So let me see. For my barium, I thought I was done with this. Where's my periodic table? I can't even see what this is. It's not even the astigmatism issue right now. This is so blurred. It didn't come in very well to where I could see it. How is that so big and yet I can't even read it? Okay, let me go back because I refuse to pay for it. Much better here, but I don't see mass number. I just see atomic number. Ooh, this is round. Once again, no mass number. Elemental haiku, really? Okay, you know what? Let me use the ones I have right in front of me. I forgot I have a periodic table. Y'all get what I'm saying, right? I'm getting the masses here. Ah, what did I do? Okay, here. Okay, you got y'all. Yeah. Anyway, just ignore it. Just ignore it. Okay, we're right here. Number of neutrons. So I'm gonna be looking at this right here. For the barium, the mass number is a big number. So it's gonna be 138. Let's see. The mass number here is 206, so I can figure out the difference here. So number of protons plus neutrons equal mass number, right? So this makes this 18. Here, I find the difference. So for barium, 138 minus 56. No, this is not on. 138 minus 56. 138 minus 56 equal, wait, what is this? 138 minus 56 equal 82. And then for lead, 206 minus 82, 124. For zinc, this is a mass number because it's an isotope, that would be 66. So for zinc, I have 66 minus 30 equal 36, right? So for my symbol, let me start with this one here. Zinc, 66, 30. For lead, Pb, 206, 82. Oxygen, 18, 8. Okay. Name of isotope, barium dash 138. Oxygen dash 18. Lead dash 206. Remember, you have the name of the element dash mass. Okay. Yeah. And that's what I have for this one here. They have your answers right here. And then remember, the things that were disproved in Dalton's atomic theory, he said that atoms were indivisible by nature. Not true. The truth is, atoms do have subatomic particles called protons, neutrons, and electrons. He said atoms of an element are identical. The truth is, isotopes are atoms of the same element, which have different masses. So the atoms are technically identical in every other way except for the masses. Okay? And like I promised, I will stop right there. When we meet next time on Thursday, we will go over atomic mass all the way to the end. And we're going to be going over the math portion of this section here. And yeah, to the end. Okay? This is all I have for today. Y'all have a nice evening or nice day, I guess. Let me go ahead and log out of here.